Okay, an introduction to energy, the first section in the notes. I go a bit further than today's lesson that unfortunately collapsed as Teams fell over. So I'm just going to walk through the idea that we discussed in the lesson before it all collapsed, and what we're going to do is just take it a little step further as well. Okay, so I'll complete the first section of the notes. So, energy, force, work, they all interlink and you can't get away from them. So this idea of energy is that we can have an amount of quantity, a probability, an ability to make things happen if we have enough energy, and the link is down to how we make it happen. So that is where our forces and this phrase work, doing work, comes from. So if you have a force, you will do work. It's all about changing the energy. Let me just click that solid focus. There we go. So we're going to look into this bit later, but we're really just kind of picking up the main things that you should have done before. But as said, one group didn't seem to have seen this at all. So the concept is basically that you have a certain amount of energy to make things happen. Okay, so energy gets stored up rather like a tank of liquid. It doesn't really matter what energy is, it's about the quantity. Okay, so effectively we have that much energy stored up. Okay, so that's our stored energy, or store of energy. So the technical phrase is energy store. But yeah, how much energy is stored up ready potentially to do something. And it will change into, to make something happen, that energy has to be used, not used up, but has to actually be used in a way that will make things happen. And that needs this needs energy transfer systems. So we have basically something that will transfer the energy. That on its own doesn't really explain anything, but we need to have this mechanism that makes it work. I should put plural because there's two of them. There's usually two or three. Not all of it turns into something we particularly want. So for example, a car, the main thing we want it to do is move. Okay, so we want the movement energy, the kinetic energy out of it. However, it also heats up the engine. We don't want that. That doesn't help us move as such. It is wasted as such. But if we were sat waiting in a car and the engine was on, then that heat is kind of useful. Okay, more than the movement. It's using energy, it's using this store to do something useful with it by transferring it into heat. So depending what we want the thing to do, what we want to actually happen, energy always gets wasted. Energy will spread out more and more and more over time, or rather more and more over every process, every step in the process. So we're always going to get what we call wasted energy, and we're always going to get useful energy. And unfortunately for most things, it is that kind of proportion. Most of our energy doesn't end up as what we want it to be. It ends up as something less useful, so that wasted. Now, if we wanted something to happen, we'll often use the phrase about a kind of a certain level. So if you can reach that energy level, okay, again notice that phrase, that level of energy, energy level. So if you get enough energy, then something can happen. So for example, here could be energy coming from a light bulb. How we get the energy to it is through photons. And if those photons have enough energy, if they have enough to overcome the work function, then they can activate that reaction. That will make the electron be released, and then you get the photoelectric effect. Okay, so this effectively is, squeeze it on the edge here, this is your, what's generally known as activation energy. Okay, it's the level needed to make something happen. So it's how, there we go, how full that tank needs to be. At the moment, there's not enough energy there. You need more energy to make whatever the process is happen. To make a puddle evaporate, bigger puddle will need a bigger total amount of energy. So it's all about whether you have enough in the tank to make your processes happen. Okay, the crucial bit is the liquid has to go somewhere. So this is why this is quite a nice, useful idea. The energy is always conserved. It goes somewhere, but not necessarily where you want it to. Now, the simple bit and the important bit is actually this is the cause. So this is how things happen. So we have to think about not how much energy, but how we are moving that energy across. And that's the ultimate process. That's the strength of this idea of energy conservation. Okay, and effectively there's only really two ways. So we'll come back to that. Bit of information for you to read through. It all links into this idea of second law of thermodynamics, okay, which is the true version. The third law of thermodynamics is the fact that we're always going to waste energy. Okay, energy gets wasted. So we'll link them all together. But the second law of thermodynamics is saying energy will transfer. So energy isn't moving, it's quantity, okay, for which we can use equations, but it links into how much it transfers across. So energy is the capacity or the ability. I'm going to go with capacity. No, we won't. Let's say ability. The ability to do work. Okay, so the vast majority of these transfer mechanisms are work. Not all of them, but nearly all of them are. So that's your process. Those are your forces making things happen, pushing things around. So we'll come back to the calculation for that and then bring the idea and so on. So in terms of how we can store energy, well, there's actually not many ways. So things can be hot, so we have thermal energy. Okay, so again, just thermal energy is all we need as title. It's not heat. That's an old-fashioned phrase. The heat tends to be heat transfer. So that's the mechanism. It links in with the mechanism, of which there's 4 different varieties. So we'll link that in a second, because that's over here. So thermal energy is inside. We'll often call things or talk about the internal energy of things. So you might want to think of that stored up inside something. Something is hot. You have heat inside you. You have a temperature that effectively measures how much energy you've got, or your average energy. Other energy that can be stored up inside, well, chemicals. Within the chemical bonds of a molecule themselves, and that ability to bond with other molecules or other atoms, that is energy that can be released, exothermic, for example. So again, chemical energy, that's also internal. Okay, so that's inside the chemical structure of the material itself. And we also have a similar one that works with that. So nuclear energy is inside the forces within the nucleus of an atom. So slightly different. So again, that's internal. Now we can kind of test materials as well. So we can stretch materials on compressed materials. So the actual spacing, not the chemical effects, but the physical effects of changing the molecular structure of things, is what we've looked at before. So strain energy, you can get away with elastic energy, but strain is better. Keep thinking strain, because then you'll get stress and strain the right way around. So this is the idea about the stretch. So the stretch or compression, we do stretch mainly. The stretching energy, that tension within the system, the tension forces, can cause that energy to be stored. Okay, so that's that whole idea. So again, it's kind of internal, although it's to do with external forces. Okay, so we have those. Then we really have 2 other kind of types as such. Some people think about vibrational and so on, but I'm going to kind of split it differently. So not internal, but some things that move, all things that move have this kinetic energy. So again, it's a store, it's keeping it, it's holding on to it, it's not doing anything with it. If something's rolling down the road steadily, imagine a football that's drifting down the road that's escaped from someone's drive. As it rolls along steadily, it's not doing anything, it's not losing the energy, it's not using that energy store to do something useful, it's just drifting along. So things that are moving have that store of energy. And then the other two types, although if you go back only about 150 years ago, three types, because we have merged them together, is down to what we call fields. And the most obvious one that we've done so far is gravitational energy. Okay, so if you want to, you could call this GPE. It's an old-fashioned word, but it saves a lot of gravitational energy writing. So we can put GPE. Okay, and that is due to what's known as a field. So there are forces which ready to cause things to happen. So the force due to gravity, the weight of an object, can make it release that energy, but if it's just sat there on a high shelf, it's not actually doing anything with the energy, it's just sat there. It's only when it falls that makes something happen. And then the other type of fields, as I say, used to be two types, but we've now realised, Sir Michael Faraday put them together, is we can have electromagnetic energy. Okay, so not radiation, but electric charges, which can link in with chemistry, to be honest. So you could merge these, you could slim these down, but well, they're kind of convenient terms, they're useful terms. So electrons repel apart. That's if you're stopping them repelling apart, then they have that energy ready to go, and as soon as you release them, then that energy is released and it can be transferred into something more useful. Magnets, very obviously, you can feel the energy as you try and repel them or pull them apart, whichever. But those are generally known as fields because the forces aren't due to actually things touching and so on. But actually, in a way, they all kind of link together. So those are kind of convenient terms. They'll all have equations that go with them. Internal energy of hot objects comes down to temperature, so that links in from temperature. That's going to bring into enthalpy and entropy, which is studied in chemistry. We study entropy as well in a more in-depth way later next year. The nuclear structure, nuclear energy, E equals mc squared. That's an equation. It's not the only one, but it's the equation. Strain energy, we've done it for stretching. So again, we've got an equation, half kx squared, where x was the extension. We know that one from GCSE. We'll do it again because it's kind of really useful. Gravitational one we got from GCSE, really useful. And then this we'll pick up next year. We'll pick it up as two separate things because it's quite a complex idea, but it links into light. Okay, so now we are in the more modern way of looking at things. As I said, how do we make that move? Well, there's two ways really. We have forces doing work. Okay, so that idea of forces causing things to happen, we tend to use two types of words, but again they're basically the same thing, just at slightly different levels. So mechanical work, okay, so if you push something around, if you kick a ball, you have done some physical work, you've used a force to make it move. And the other one is where you've got this idea of thermal, so we have these collisions. Okay, so we're talking about particles rather than large scale. So particles doing work. Let's make that doing work. Okay, now the particles themselves, if they're traveling around, aren't doing anything. So it's to do with the word to think about, or the thing to look out for, is collisions. So electrons collide into ions, cause wires to get hot, for example, if the ions are the wire ions. Electrons smacking into a screen cause it to give out light in your old TVs and cathode ray oscilloscopes and things like that, and so on. But the last one is this idea of radiation. And so when we're talking about radiation, again, we can use the older-fashioned way of waves, electromagnetic radiation, kind of links things in. But more conveniently, probably, the easiest way to think of it is photons. radiating in different directions. So effectively we've got work, okay, these are basically things involving forces, okay, or you've just got this idea of packets of energy, quantity of energy, so nothing actually going. These cannot collide, these are where the energy is absorbed out of them. Okay, so the subtle different ways. Most things involve stuff being pushed around. Sorry, let's put that in. So most of the things that transfer energy involve work. But light is a very useful way of thinking of things as well. So transferring energy from somewhere to somewhere else. Now it brings us into the idea of work done. Now the crucial thing is, and I'm just going to link it into this side, so maybe on a post-it, I can't remember if you've got blank side or not, but if we think about the force on things, we've done this concept when we looked at springs. But if you had forces making things move, so let's think of it as position, okay, if you have a force continuously moving something along, then its position will change at a nice steady rate as long as you keep pushing it. So a mouse, for example, yeah, I've given it energy and I'm doing a certain amount of energy, and up to a point, very simply, again, as I've said before with force graphs, the area underneath will represent, or give you a value for rather, this will give you work done. Okay, it's the work that has been done by the force. Okay, so that is that whole point of it. So that's where it comes from. But it gives us the most important, really simple, the simple ones are always the important one, really simple idea of what we mean by energy. And we do it really in terms of that transfer mechanism. So work is, again, notice it's not work done, it's just work, force times distance moved, okay, in, and this is the crucial bit, in the direction of the force. Okay, so if it doesn't go in a straight line, it's still about the distance in the force. So for example, you have wind blowing on a sailboat, the yacht or the dinghy will go at an angle, so it's not always in the same direction as the force, but how much energy it has gained is in the direction of the force. So actually what we're talking about here is displacement, okay, hence that. So truly, and again this isn't quite right on the data sheet and it's really annoying, this is force times displacement, okay. They've used an X, which is a bit of a problem because we use that for extension. This isn't extension, and it's not D because firstly it wouldn't fit with SUVAT, so hence S for SUVAT, but it isn't D because D is used for force times perpendicular distance on the data sheet, moments of a force. So this is not moments, don't let it get you confused, don't kind of go, oh, same equation. It's not, they mean different things. So this one is in the same direction, they have to be in the same direction, so they're both vector quantities, whereas the distance is just a perpendicular distance. It's not necessarily the idea of vector, it's how far you are separated away, so it's a distance, not a displacement. Okay, so a little bit extra. Now in real life we tend to often not have them in the same direction. However, I would really concentrate on that. Keep that as your equation. We used to have workers find dinosaurs at GCSE, but it's let's go a bit higher than that. Now that bit is very important. It is the fundamental equation of physics, the basis of all physical things happening in the universe, in nature. Okay, so really important. However, mathematically and in terms of questions, you'll often get something like this. So here's a nice snowy day, here's a sledge, here's someone pulling on the string. what you're doing is, of course, you're lifting it up a bit and you're pulling it forwards a bit. Okay, so the useful thing that you're after is not the lifting up. The useful thing is the how far you're moving it along. Okay, so if your sled moves distance s, then we really want to think about that in terms of the force, and we can do it in two ways. Most people will tend to do the latter way, the second one, but I'm going to give you the first one so you give that idea to start with. So we have s, it is a vector, it's going along that way. We have, or we can think of the direction of the quantity of s that is moving parallel to the force. Okay, so if I do that, a little bit big there, okay, then actually that version there, that's going to be s in direction of force. Okay, and sometimes that's convenient. So that length, reduced displacement multiplied by the force will give you a reduced amount of work done. Okay, now if we put those in and use the mathematics of that, I'm sure you will recognize that s is part of, as a component of s. Okay, so s is the biggest side, therefore I'm going to multiply by the right thing, and in our equation there, that's our angle. Again, often done from horizontal. Cos. Okay, so s times the cos of the original s, the actual displacement. Now, a lot of people use that for useful things, don't forget about it, but most people will tend to, what they'll do is they'll take the force and they'll move it. Notice the right angle is in a different place here. Okay, you're wanting to know what component of force is in that direction. Okay, so our f dash based on the original f. Now again, if that's theta, then we will just find that f dash equals f cos theta as well. It's exactly the same multiplying factor, so it doesn't matter which way you do it. Okay, and so that will end up with work. Okay, often given that just that w, but if you want to write work, by all means, f s cos theta. Okay, and it's vast majority of the time, particularly in year one, all the stuff is kind of done from the horizontal, so that's always the right angle, it's always cos. Now, just be careful, because in the data book it is written as fx cos theta. You can probably see the problem straight away. When people are in a rush in the exam, they just say f cos theta. F multiplied, no, it's not multiplied by. So x is a really bad example. Go to your data book, write in this next to it. Make sure you leave a gap or put a dot or something to kind of show multiplication. Okay, or product, more to correctly, that's the symbol for. So yeah, just be wary, not multiply. Okay, so it's not that. Just be really, really careful of that. Okay, now what we'll do is a small derivation. It's a really kind of useful one, just to pick up. But again, it's because we often use the word power, and it's quite useful. So, power is defined as energy, in terms of energy. But the key point is how quickly it's transferred. So if we go back to my original diagram, how much flows in or out, great, useful, but how quickly it flows in and out is usually more useful. So if the rate of energy transferred by photons is bigger, I'm getting more photons per second, what happens? You detect brighter light. Okay, so the brightness of a light bulb is its power. That's why light bulbs are measured in power. So power is a useful concept because it tells us the rate at which you are emptying your tank or transferring that tank, the contents of your tank, to somewhere else. So your store is emptying at what rate. Okay, and that's a really useful kind of idea. So it's the rate of energy transfer is one way of looking at it, or more usefully, because it gives us to the link, it's the equals rate of work done. Work being done, often shortened to work done. Okay, so what we end up with is P is just simply shown as W for work, not watts. Be careful, power is in watts, work is in joules, divided by time. Now I should say, while I've mentioned that, work is in joules because that is what is how much is being transferred. Energy is obviously measured in joules as well, so just be a little careful of that. That's in seconds, that will be in watts, and just hinting that 1 watt equals 1 joule per second. So every second 1 joule gives us 1 watt. So kind of a useful little conversion there. We'll talk about that quite a lot. You're often given that hint in questions. It might say 20,000 photons are hitting a screen every second. What is the rate of energy transfer? And what they're after is the power, but they'll say the rate of energy transfer. So it's this idea of energy per second. Well, you've got the number of particles per second, so you just need how much energy all the particles each second carry. So that kind of idea. But yeah, they're equal in size, but they're not the same thing. So I'm going to pick that up a little bit, okay, because these are slightly different. As I said, power equals work over time. It equals energy transfer. So not energy, it's how much energy changes per second. Okay, so they're actually slightly different. Note it is not, so I should put an NB there, not a change in work. Work is a process. How much your energy store changes is what we're talking about. So we've got change in energy because work is being done. Okay, so a little bit of really kind of crucial difference in your head to clarify them. The quantity is the same. So 20 million joules of work means that your tank empties by 20 million joules. Okay, so it's not a hard thing. But it's quite a convenient way of looking at it. So I've got a really nice example, and again, this is on your data sheet, so just want to explain where it comes from. We'll often talk about the power of things, and this is starting to get into the hints that actually we can start to involve real life things. So when we did SUVAT, we assumed there were no external forces, but there are. You know, if you're moving through air, you are going to get some drag. Okay, so as we get a velocity moving along, you'll get drag. If you change velocity, you'll change the drag, and that has an overall effect. Now, because of that, in real life, your tank will keep emptying just to move at a steady speed. Okay, so we're not changing the amount of kinetic energy. Okay, we're not changing the work being done, but we are emptying our tank. Okay, and the reason we're not changing the kinetic energy is it changes into, or it is transferred into kinetic energy, which is then given out into other tanks. Okay, so we have wasted energy, the energy being wasted all the time. If you're at a steady speed, okay, if you're at steady speed, you're continuously supplying energy to the engine, which then continuously wastes it to drag and other things, heating, radio, etc. I should point out, not just this, we have, back to our second law of thermodynamics, we can also increase the heat. So if you're heating up your car inside, that also increases the amount of energy that it needs to be going to your engine to then generate that heat and generate the force to push against the air, and so it all keeps adding up. So the more things you turn on, the more your energy, the rate of energy transfer from your tank is. So the greater the power of your engine. What that means is, if you turn your lights on, you're going to burn petrol faster. You're just conserving energy. You need more energy to create the light and the motion than you do just moving. So therefore you are going to need greater energy in your tank to start with. Okay, so the logic is all there. But more importantly, there's a useful little thing that takes that a step further. So if we want to work out how big an engine you need, well, we need to think about this idea of the work done due to the forces that act on it. Okay, so if we take that, we'll just use Z power is work over time. Okay, but work equals Fs. Okay, I'm going to stick with S rather than the data book version. So what that means is power equals Fs over T. Okay, not delta. So displacement per second is velocity. So actually power equals, I should do some processes going on here. So that's substitute that into our first equation, and you will get to that second one, and that's going to equal force times velocity. And that's on your data sheet. Short little derivation, just putting two ideas together. But what that means is if you want to drive at a bigger velocity, you will need a bigger power engine. What do I mean by that? Your engine will empty the fuel tank faster. That's what we mean by power. You don't necessarily need a bigger engine, you're just going to empty the tank at a greater rate. Okay? If you have a car, and we'll build up to this in another section, if you've got a car that hits more air, so if you've got an SUV or a Jeep or something like that, or a truck, it hits a lot more air. And if it hits a lot more air, you've got a much bigger force, therefore again you burn fuel faster. So by limiting speed, by having a more aerodynamic car, by physics alone, no matter how good your car is, those two factors themselves will reduce the rate at which you empty your tank. And I believe there was something on Top Gear, not that I really watch it, but I think they drove the length of the UK to north of Scotland and back again on a single tank of petrol from three very different cars, literally by just keeping the velocity down. Okay, I think one of them was one of those BMW things. Okay, so really kind of useful, but I'm just going to finish with one health warning, which is where this comes in. Don't automatically assume this, and I think this is why this is a dangerous equation. Okay, that's far more useful. Get rid of the cos theta. So WFS, work is force times displacement, is far more powerful, because that is not always true when you get onto the harder level stuff. So, example, if you've got something traveling up a slope at a steady speed, okay, your engine needs to produce a force. That force, for this to be a steady speed in equilibrium, okay, not changing its motion, so at equilibrium, what you'll find is that your equilibrium is that your force has to counter the drag, but you've also used extra fuel to get up a hill, because you've also got to fight the weight of the car. On the flat you don't. Okay, that does not make a difference. The fact you've got a heavier car does not make a difference to energy traveling at a constant speed. Next topic we'll look at acceleration, so we'll leave all that out of it for a bit. But if we look at this, for example, then of course in terms of our, I'll put that on the flat, in terms of this diagonal force, we have some of that going across, and I'll draw it down conveniently here. You will have some force in opposition to that. So that one plus that one has to equal that one to be a steady speed. Okay, so that's my component, not horizontally here because that's not convenient, but component along the slope. So if you have things on a slope, this is really important because this happens quite a lot. They will test you on things like that. They often have things on a slope. It makes it difficult. Then what we have is the force here will actually be working against the engine as it goes up. Okay, so it's I should make that clear because it's not very clear from my diagram. So going up the slope, that component, slope not slop, that component will work against it, and if you do the maths of that, that angle is the same as that angle. Okay, so that's theta, it's opposite, that's going to equal mg, because that's your force, times by sine of theta. Okay, because it's the opposite to the angle, so it's the sine. So notice, not cos theta, so it doesn't work if you're doing that. It only works if you are pulling something along the road, along the flat with a string, that kind of thing. Okay, so just be wary of that equation. Just use Fs and think about your angles, break them down. Anything on a slope like this should cause alarm bells. Okay, so crucial bit, if v is constant, let's make that clearer, and that's the crucial bit, so not accelerating, because then it just gets harder, then F equals this big F equals F resistance plus mg sine theta. Okay, so that's what you're doing. If it was going down the slope, let's just point that out, then your engine doesn't have to work as hard. You rolling downhill won't use as much petrol. Why? Because the component is still down the hill. The resistance will be going up the hill now, so these two arrows will face over, swap over. Okay, but the force needed from the engine is smaller, because although it must cancel out the resistance still, assuming it's the same speed, you're being helped by the component rather than being hindered by it. Okay, so this is helping you. This will reduce, that'll be part of your total force, whereas at the moment those two add up to equal the force. So if you subtract that one from that, you'll get that. Okay, that's the kind of idea for going down the slope. So the same kind of stuff, but stick with that basic idea. It is so much more useful. Okay, and I'll stop it there. So that's a big idea, lots of stuff, and can give us lots of explanations. Crucially, there's only two equations. Other than adding up forces, you've got force times displacement is work, and you've got the idea of power, the rate of work, gives you F times V for a moving object. Those are your two main ones. Power as rate of change of energy is frequently used all over the place, not just to do with motion. Okay, so that equation features not just here, so it's kind of universal. Okay, so if you think of it as its definition, that's a really kind of important idea, but it's, yeah, it just assumes that all the time. But the two usable equations, that one there and that one down there, are the most important for motion. I almost forgot the most important thing, which is about the work. So if we use this as our resultant force, okay, this total force here of the resistance plus the component, or going down the slope subtract the component, then you're going to end up with that whole concept of just work done, how quickly you're using your fuel is just going to be that whole thing. So you've just got you know, F res plus mg sine theta times by however far it goes up the slope. Okay, so a useful kind of thing, but again, it's just adding up forces, but just be wary, it's not cos. Okay, now there are loads of questions in the back. Just to finish off, have a practice all these. Some of them are really nice and straightforward. Okay, so they are easy to do. I've got my my notes and things in here. Here we go. Work done by gravity, because there's a force making a rock fall. Okay, and things like that. And then we've got others a little bit harder. So I build up to things on slopes. Okay, so there's quite a lot about cyclists going up and down slopes. Okay, again, power is not about the size of the engine, it is how quickly you burn your energy. So yeah, if you do watch cycling, then you'll know it's all about the power output of people on their pedals. Thank you very much.